Welcome, dear listener, to this journey through the wonders of deep space. Before we embark, I invite you to pause for a moment and share in the comments where in the world you're tuning in from and what time of day it is for you. It's a delight to have you here, drifting off to sleep while pondering the cosmos with fellow explorers from all across this pale blue dot we call home. If you find yourself enjoying this gentle meander through the universe, consider subscribing. There are always more stories waiting to be told. As we settle in, let your mind wander up to the night sky above. No matter where or when you are, those stars have been our constant companions, sparking wonder in humans for as long as we've walked this earth. Ancient eyes gazed up at the same constellations we see today, weaving stories and meaning into the patterns of the cosmos. For millennia, the true nature of those twinkling lights remained a mystery. With each passing generation, we've slowly peeled back the layers of the unknown to reveal the astonishing truths that lie beyond our world. Our ancestors' first steps towards understanding began with careful observation, the patient watching and recording of the heavens. In the dusty reaches of the Middle East, Babylonian priests meticulously tracked the wanderings of planets against the fixed stars, believing they could divine the will of the gods in their motions. They laid the foundations of astronomy, mathematics, and timekeeping that still underpin our modern world. As they looked up at a sky ablaze with the light of 1,000 suns, could they have imagined the vast near-empty gulfs that separate those stars? The ancient Greeks built upon this tradition, weaving keen observations with daring philosophical debates about the nature of the universe. Aristotle, one of the most brilliant minds of antiquity, proposed an ordered cosmos with the Earth at the centre, encircled by concentric crystalline spheres carrying the celestial bodies. His model, refined by Ptolemy, would reign as orthodoxy for centuries. They had no conception of the true scale of the universe. To them, the starry firmament marked the very edges of existence. It would take a cascade of radical thinkers to topple this Earth-centric view. In the 1500s, Nicholas Copernicus proposed a heliocentric model, a sun-centered universe in which the Earth was just another planet. It was a daring idea that demoted our world from the centre of creation, and it would set the stage for a revolution in our understanding of the cosmos. But Copernicus's ideas remained abstract, mathematical theories lacking physical proof. That would require a new way of seeing the universe. In the early 1600s, in a eureka moment, Galileo Galilei turned a new Dutch invention called the telescope towards the heavens, and what he saw would change our view of the universe forever. Where others saw only points of light, Galileo spied mountains and craters on the moon, spots drifting across the face of the sun, moons orbiting Jupiter, and shimmering rings encircling Saturn. These observations dealt a shattering blow to the notion of heavenly perfection. Moreover, the moons of Jupiter demonstrated that not everything revolved around the Earth. It was the first empirical evidence for Copernicus' heliocentric hypothesis. In the centuries that followed, astronomers methodically mapped the stars with ever greater precision, cataloguing their positions and apparent brightnesses. They became intimately familiar with every inch of the celestial sphere, detecting subtle changes and anomalies. In the late 1700s, William Herschel nearly doubled the size of the known solar system with his serendipitous discovery of Uranus, the first new planet found since antiquity. The heavens, it seemed, still held surprises. However, the question of the star's true distance remained elusive. A possible answer came in the concept of parallax, the apparent shift in an object's position when viewed from different vantage points. Astronomers reasoned that if the Earth orbited the Sun, nearby stars should appear to wiggle slightly against the distant background over the course of a year. But no matter how carefully they looked, no parallax could be detected. Either the Earth was stationary or the stars were so remote that their parallax was immeasurably tiny. It would take the painstaking work of Friedrich Bessel in the mid-1800s to finally detect this elusive stellar parallax. Turning the finest instruments of the time on a nearby star called 61 Cygni, Bessel measured a minuscule annual shift, indicating a truly vast distance between Earth and the stars. At last, the cosmic scale was coming into focus, and it was grander than anyone had dared to imagine. As telescopes grew larger and more sophisticated, they began to unveil the diverse nature of the stars themselves. Astronomers noticed a wide range of colours and brightnesses, hinting at underlying physical differences. The advent of spectroscopy, the splitting of light into its constituent colours, let them read the chemical signatures written in the star's light. To their astonishment, they found that stars were composed of the same elements found on Earth, albeit in alien proportions and under extreme conditions. We were more intimately connected to the cosmos than we had ever imagined. Among the most fascinating classes of stars were the Cepheid variables, which pulsated in brightness over regular periods. In the early 1900s, astronomer Henrietta Swan Leavitt studied thousands of these beacons and uncovered a remarkable pattern. Brighter Cepheids had longer pulsation periods. This period-luminosity relationship meant that by timing a Cepheid's pulses, one could deduce its intrinsic brightness. By comparing this to its apparent brightness, astronomers could calculate its distance. Leavitt had found a standard candle to illuminate the universe's scale. One astronomer who seized upon this discovery was Edwin Hubble. In the 1920s, he aimed the world's largest telescope at the time towards mysterious patches of light known as spiral nebulae. Peering at the hazy spiral of Andromeda, Hubble spotted a Cepheid variable and, using Leavitt's yardstick, calculated its distance. To his shock, it lay far beyond the bounds of the Milky Way, in the uncharted waters of intergalactic space. Andromeda wasn't a nebula within our galaxy, but a galaxy in its own right. The universe, Hubble realised, was a far vaster place than we had imagined, filled with island universes like our own. Hubble continued to measure the distances to more galaxies and noticed a curious trend. The farther a galaxy was, the more its light was shifted towards the red end of the spectrum. Just as the pitch of a receding train's whistle drops, this redshift indicated that distant galaxies were rushing away from us. Even more astonishingly, their recession velocities increased linearly with distance, a relationship now known as Hubble's law. The inescapable conclusion was that the universe itself was expanding, carrying galaxies along with it like raisins in a rising loaf of bread. This monumental discovery pointed back to an even more profound origin. If the universe was expanding, then in the past it must have been smaller. Extrapolating backwards in time, it seemed that all of space and time began in an infinitely dense point, a cosmic seed from which the universe unfurled. This was the first intimation of the Big Bang, the titanic event that marked the birth of the cosmos as we know it. As the 20th century progressed, astronomers continued to refine this model of a dynamic, evolving universe. In 1965, Arno Penzias and Robert Wilson stumbled upon a faint microwave glow suffusing the entire sky, a relic of the early universe's searing heat. This cosmic microwave background, a mere 2.7 degrees above absolute zero, offered a glimpse of the universe as it was 13.8 billion years ago, a mere 380,000 years after the Big Bang. Its discovery was a triumphant confirmation of the Big Bang model. In the decades since, new instruments have opened new windows on the cosmos. Space telescopes like Hubble, free from the blurring effects of Earth's atmosphere, have captured breathtaking images of the universe in unprecedented detail. From the delicate, colourful structures of nearby nebulae to the deepest images of the remote universe, each new observation has revealed new wonders and raised new questions. One of the most profound came from the Hubble Deep Field, an image that peered into a seemingly empty sliver of sky for over 10 days. The result was astounding. Nearly 3,000 galaxies of various shapes and sizes, each containing billions of stars stretched back to the very edges of the observable universe. If one tiny patch held such multitudes, how many galaxies could the whole universe hold? Billions? Trillions? The true scope of the cosmos staggers the imagination. And yet, for all the wonders we've discovered, we've barely scratched the surface of the universe's mysteries. We now know that the luminous matter we can see, stars, galaxies, nebulae, makes up a mere 5% of the universe. The rest is composed of dark matter, an invisible form of matter that we can detect only through its gravitational influence, and dark energy, a mysterious force that seems to be accelerating the expansion of the universe itself. We're only just beginning to grapple with these enigmas. Other questions remain tantalizingly open. Could life, perhaps even intelligent life, have arisen elsewhere in this vast cosmos? With each new exoplanet we discover, the possibility seems more real. What wonders might await us on those alien shores, and what might lie beyond the bounds of the observable universe, forever hidden from us by the very expansion of space? As we drift off to sleep, let us dream of the wonders yet to come. The story of astronomy is one of ever-expanding horizons, each new discovery opening up new frontiers of the unknown. It is a story that reminds us of our place in the grand sweep of cosmic history, a story that has been written in the stars since long before we raised our eyes to the night sky. Though we may feel small in the face of the universe's immensity, we are also a part of its grand unfolding. The calcium in our bones, the iron in our blood, the very atoms that make up our being, all were forged in the crucibles of ancient stars. We are stardust given consciousness, the universe reflecting on itself. In seeking to understand the cosmos, we are ultimately seeking to understand ourselves. So as you slip into slumber, take comfort in the knowledge that the same stars that wheel overhead tonight have shone down on countless generations before us and will continue to shine long after we are gone. Our time here may be fleeting, but our connection to the cosmos is eternal. Dream well, dear listener, and may the wonders of the universe fill your dreams. As we ponder the vast expanse of the cosmos, it's humbling to realize that our journey of discovery has only just begun. With each passing decade, new marvels come to light, challenging our assumptions and igniting our curiosity anew. One of the most astonishing revelations of recent times is the discovery of exoplanets, worlds orbiting distant stars. The first confirmed exoplanet around a sun-like star, 51 Pegasi b, was discovered in 1995 by Michel Mayor and Didier Queloz. This strange world, about half the mass of Jupiter, orbits its star so closely that its year lasts a mere 4 Earth days. Its surface temperature likely soars above 1,000 degrees Celsius, hot enough to melt iron. This scorching hot Jupiter defied our expectations of what a planetary system should look like. As planet hunting techniques improved, astronomers began to find exoplanets by the hundreds, then thousands. NASA's Kepler Space Telescope, launched in 2009, discovered over 2,600 confirmed exoplanets during its 9-year mission by precisely measuring the tiny dip in a star's brightness as a planet transits across its face. What began as a trickle of bizarre worlds soon became a deluge of planetary diversity beyond our wildest dreams. We found worlds where molten rock rains from the sky, where winds howl at thousands of miles per hour, and where precious gems may condense in the atmospheres like celestial jewels. We found super-Earths, mini-Neptunes and gas giants that make Jupiter seem small by comparison. We've even found planets orbiting binary star systems, like Tatooine in the Star Wars universe, sci-fi made real. Perhaps most tantalizing of all, we've found planets that orbit within their star's habitable zone, where liquid water could potentially exist on the surface. In 2015, astronomers discovered an Earth-sized planet around the star Proxima Centauri, our Sun's nearest neighbour at just 4.24 light-years away. This world, named Proxima b, orbits in the habitable zone of its dim red dwarf star. Could alien life flourish beneath its ruddy light? The question tingles the imagination. As we drift through the galaxy of exoplanets in our minds, it's easy to forget that each one of these worlds is a complete planet unto itself, with its own geology, atmosphere and potential for harbouring life. The sheer abundance of planets tells us that our solar system is not unique, that the building blocks of worlds are scattered widely across the cosmos. And if planets are common, what about life itself? The search for extraterrestrial life is one of the great scientific quests of our time. While we have yet to find definitive proof, we've discovered tantalizing hints that life could arise in the most unexpected places. In the 1970s, the Viking landers conducted experiments to search for microbes in the Martian soil. While the results were inconclusive, they opened our minds to the possibility of life on other worlds in our solar system. More recently, NASA's Cassini spacecraft revealed the presence of hydrothermal vents on the floor of Saturn's moon Enceladus, spewing plumes of water vapour and organic compounds into space. Jupiter's moon, Europa, also shows evidence of a subsurface ocean beneath its icy shell, which could potentially host microbial life. The moons of the outer solar system, once thought to be frozen, barren wastelands, now beckon as oases for life to take hold. But what about intelligent life? Civilizations that, like us, gaze up at the stars and wonder if they are alone. The question has captivated humans for centuries, From the fantastical tales of Lucian of Samosata in the 2nd century AD to the modern-day search for extraterrestrial intelligence, or SETI. In 1960, astronomer Frank Drake conducted the first modern SETI experiment, Project Ozma, listening for radio signals from 2 nearby sun-like stars. While he didn't detect any alien transmissions, the era of SETI had begun. In the decades since, astronomers have searched the skies with ever more sophisticated radio telescopes, listening for whispers of distant civilizations among the static. In 1977, the Ohio State University's Big Ear radio telescope detected a powerful 72-second signal that seemed to originate from the constellation Sagittarius. The signal, dubbed the WOW signal, after the notation made by astronomer Jerry Eman on the computer printout, remains unexplained to this day. Was it a fleeting transmission from an alien intelligence, or merely a glitch in the telescope's electronics? The tantalizing uncertainty keeps us searching. As our technology advances, so too does our approach to SETI. Instead of merely listening, some astronomers propose that we should be actively transmitting messages to any civilizations that might be out there. In 1974, the Arecibo radio telescope in Puerto Rico broadcast a message towards the globular cluster M13, a collection of several 100,000 stars some 25,000 light-years away. The message, designed by Frank Drake and Carl Sagan, included basic information about our solar system, DNA, and a crude diagram of a human figure. Whether anyone is around to receive it remains an open question. Perhaps the most profound realization to emerge from our search for cosmic companions is the sheer vastness of space and time. Even if intelligent life is abundant in the universe, the distances between stars are so immense that any 2 civilizations might be separated by thousands or millions of light-years. And because a signal can only travel at the speed of light, any message we receive would be a postcard from the distant past, a ghostly echo of a civilization that might have long since moved on or faded away. And yet, the search continues. In the coming decades, new telescopes like the Square Kilometre Array will probe the skies with unprecedented sensitivity, potentially detecting the faint murmur of civilizations beyond our cosmic shores. And as we launch new probes and satellites to study the moons and planets of our solar system, we may finally answer the question of whether life has taken root elsewhere in our celestial neighbourhood. As we lie here in the dark, our minds adrift in the currents of space and time, it's easy to feel small and alone in the vastness of the cosmos. But in a way, that realization is also profoundly comforting. If life and intelligence are rare in the universe, then our existence is all the more precious and remarkable. And if we do share this cosmos with other minds, then perhaps we are all united in our common journey to understand this strange and beautiful universe we find ourselves in. As sleep slowly enfolds us, we can take solace in the knowledge that, no matter what the future holds, we are a part of something much grander than ourselves. The story of the universe is still being written, and we have the privilege of being a footnote in that cosmic tome. So let us dream of the wonders yet to be discovered, and the marvels that await us in the vast expanse of space and time. Good night, and may your dreams be as boundless as the cosmos itself. Our journey through the cosmos now brings us to one of the most peculiar and enigmatic denizens of deep space: black holes. These extraordinary objects have captivated the imaginations of scientists and the public alike, and for good reason. They represent the very extremes of physics, where our understanding of the universe is pushed to its limits. The story of black holes begins, as many tales in modern physics do, with Albert Einstein. In 1915, Einstein unveiled his groundbreaking theory of general relativity, which revolutionized our understanding of gravity. According to Einstein, gravity is not a force as Newton had described, but rather a curvature of space-time itself. Massive objects like stars and planets cause dips or wells in the fabric of space-time, and other objects follow these curves, giving the appearance of being attracted by gravity. Einstein's equations allowed for the possibility of a most unusual cosmic phenomenon, a point in space where mass is so concentrated and gravity so extreme that nothing, not even light, can escape its grip. These points came to be known as black holes, a term coined in the 1960s by physicist John Wheeler. But the idea of a dark star from which light could not escape dates back to the 18th century and the work of Jean Michel and Pierre-Simon Laplace. For many years, black holes remained in the realm of theoretical speculation. Einstein himself doubted whether such extreme objects could actually exist in nature. But as astronomers probed the cosmos with increasingly sophisticated tools, they began to find hints of these dark behemoths lurking in the depths of space. One of the first clues came from the discovery of quasars in the early 1960s. Quasars, or quasi-stellar radio sources, are incredibly bright objects billions of light-years away. They emit more energy than hundreds of galaxies combined, yet they're so compact they appear point-like, like stars. Astronomers puzzled over what could power such intense luminosity from such small regions. The answer, it turned out, lay in the extreme environment around supermassive black holes. As matter spirals towards a black hole, it forms a swirling disk called an accretion disk. Friction and magnetic fields in the disk cause the matter to heat up to incredible temperatures, glowing brightly across the electromagnetic spectrum before it crosses the black hole's event horizon, the point of no return. Quasars, we now understand, are the brilliant beacons of supermassive black holes voraciously consuming matter in the cores of distant galaxies. As the matter falls in, some of it is redirected away from the black hole in powerful jets of plasma moving at nearly the speed of light, which can extend hundreds of thousands of light-years into space. But not all black holes are supermassive monsters weighing millions or billions of times the mass of our Sun. Smaller black holes, a few to a few dozen times the Sun's mass, can form from the explosive deaths of massive stars. When a star much more massive than our Sun runs out of fuel, it no longer has the energy to support its own weight. Its core collapses, and the outer layers are blasted away in a tremendous supernova explosion. If the collapsing core is massive enough, it can be crushed down into a black hole. The first strong evidence for these stellar mass black holes came in the 1970s with the discovery of Cygnus X1. This powerful X-ray source was found to be a binary system, where a blue supergiant star orbits an unseen companion. The intensity of the X-rays and the motion of the visible star suggested that the hidden object was a black hole about 15 times the mass of the Sun. Since then, dozens of similar X-ray binaries have been identified, each likely harbouring a stellar mass black hole siphoning gas from its companion star. But how can we be sure these invisible objects are really black holes and not something else, like neutron stars? The key lies in measuring the mass of the unseen object. Neutron stars, the ultra-dense remnants of supernova explosions, have a strict upper limit to their mass, about 3 times the mass of the Sun. Anything heavier, and the force of gravity overwhelms all others, crushing the object into a black hole. So if astronomers measure the mass of the invisible object and find it exceeds this limit, they can be confident they've found a black hole. These mass measurements are made by carefully observing the visible star's orbit. Just as planets orbiting the Sun trace out ellipses, stars orbiting black holes also follow elliptical paths. By measuring the star's velocity and the size of its orbit, astronomers can calculate the mass of its unseen companion using Kepler's laws of orbital motion, the same principles that govern the motions of the planets in our solar system. In the 1990s, astronomers using the Hubble Space Telescope applied this technique to make the first definitive identification of a black hole. They studied a pair of stars orbiting each other in the constellation Cygnus, a system known as 404 Cygni. By carefully tracking the star's motions, they calculated that one of the objects was at least 6 times the mass of the Sun. Too massive to be a neutron star, it could only be a black hole. Since this groundbreaking discovery, Hubble and other telescopes have conducted a cosmic census, identifying numerous black holes in our Milky Way galaxy and beyond. We now know that black holes, once thought to be mere mathematical curiosities, are very real and surprisingly common. But the most compelling evidence for black holes came just a few years ago, thanks to a remarkable feat of science and engineering. In 2015, after decades of development, the Laser Interferometer Gravitational Wave Observatory LIGO made the first ever direct detection of gravitational waves ripples in the fabric of space-time itself. The source of these waves was the cataclysmic collision of 2 black holes, each about 30 times the mass of the Sun, that occurred 1.3 billion years ago. As these dense objects spiraled inward and merged, they radiated energy in the form of gravitational waves, sending shudders through the cosmos at the speed of light. By the time these waves reached Earth, they were incredibly faint, stretching and squeezing space by less than the width of an atomic nucleus. But LIGO, with its exquisitely sensitive detectors, was able to pick up this subtle signal. The observation was a stunning confirmation of Einstein's century-old prediction and a triumphant capstone to the quest to prove the existence of black holes. Since that first detection, LIGO and its European counterpart Virgo have observed the gravitational waves from numerous black hole mergers, opening a new window onto these exotic objects and ushering in the era of multi-messenger astronomy. But for all we've learned about black holes, they remain among the most mysterious objects in the cosmos. What happens to matter that falls into a black hole? Does it disappear forever from our universe? Or does it emerge somewhere else, perhaps in another dimension or another universe entirely? And what lies at the heart of a black hole, at the point known as the singularity? Here, our current theories break down. General relativity predicts that at the singularity, space and time cease to exist, and the laws of physics as we know them no longer apply. To truly understand what happens in these extreme environments, we'll need a quantum theory of gravity, a theory of everything that has eluded scientists for generations. Perhaps the most fascinating and perplexing question about black holes is whether they destroy information. In quantum mechanics, information is never lost. It can be transformed and scrambled, but never erased. But when matter falls into a black hole, it seems to disappear completely, taking all its information with it. This presents a profound paradox that has puzzled physicists for decades. In the 1970s, Stephen Hawking made a startling discovery that offered a potential resolution. Using quantum theory, he showed that black holes are not entirely black. They can emit radiation, slowly evaporating over time. This Hawking radiation carries away energy from the black hole, causing it to shrink and ultimately perhaps to disappear entirely. But what happens to the information contained in the matter that fell into the black hole? If it truly vanishes, it would violate a fundamental principle of quantum mechanics. This conundrum, known as the black hole information paradox, has been a major focus of research in theoretical physics. Some scientists propose that the information is not lost, but is instead stored on the surface of the black hole in a sort of cosmic hologram. Others suggest that the information escapes in the Hawking radiation, but in a highly scrambled form that is practically impossible to decipher. Still others propose that black holes are actually fuzzballs of strings, the hypothetical fundamental building blocks of the universe according to string theory. The true nature of black holes and the fate of information that falls into them remain open questions, tantalizing puzzles that may hold the key to unifying quantum mechanics and general relativity. As we continue to study these enigmatic objects with increasingly advanced telescopes and detectors, we may inch closer to resolving these deep mysteries. Black holes, once mere figments of theoretical fancy, have emerged as central players in the cosmic drama. They are the ultimate laboratories for testing our understanding of physics in the most extreme environments imaginable. They are the engines powering the most luminous beacons in the universe. They are the sculptors of galaxies, shaping the evolution of the cosmos on the grandest scales. And yet, for all their importance and intrigue, black holes remain cloaked in mystery, their innermost secrets hidden behind an impenetrable veil. As we ponder these cosmic enigmas, we're reminded of how much we have yet to learn about the universe we inhabit. Each discovery raises new questions, inviting us to venture ever deeper into the unknown. As we drift off to sleep, our minds can wander freely, unencumbered by the constraints of what is known and what is possible. In our dreams, we can explore the strange and wonderful possibilities that lurk in the depths of space and time. We can imagine diving into a black hole, experiencing the warping of space and the slowing of time as we approach the singularity. We can envision a universe filled with wormholes, shortcuts through space-time connecting distant points like cosmic portals. We can contemplate the multiverse, an infinite ensemble of universes, each with its own unique physical laws and constants. In the realm of dreams, the only limit is our imagination. And as we've seen throughout the history of science, it is often the dreamers, the ones who dare to imagine the impossible, who end up expanding the frontiers of our knowledge. From the ancient astronomers who first charted the stars to the modern physicists probing the nature of reality itself, it has been the fearless explorers, the ones willing to venture into the unknown, who have driven our understanding of the cosmos forward. So as you slip into slumber, Let your mind wander to the farthest reaches of space and time. Dream of the wonders that await us in the cosmic depths, the secrets yet to be unveiled, the discoveries yet to be made. And know that with each passing day, we are slowly but surely unravelling the mysteries of the universe, one observation, one equation, one dream at a time. For in the end, the story of astronomy is the story of us, a curious, adventurous species, forever seeking to understand our place in the grand cosmic tapestry. From our first glances at the starry sky to our most ambitious space missions, we have been driven by a profound longing to know the unknown, to fathom the unfathomable, to touch the untouchable. It is a journey that has taken us from the comfort of our pale blue dot to the farthest reaches of the observable universe, and one that will continue as long as we dare to dream. So dream on, dear listener, and let the wonders of the cosmos be your guide. For in the depths of space, there are still countless mysteries waiting to be solved, countless worlds waiting to be explored, countless stories waiting to be told, and with each new discovery, each new adventure, we come one step closer to understanding our place in the grand cosmic scheme. As you drift off into the realm of dreams, carry with you the awe and wonder of the universe we inhabit. Let the stars be your beacons, the planets your stepping stones, and the vast expanse of space your playground. And know that wherever your dreams may take you, the cosmos will always be there, inviting you to explore its infinite possibilities. Good night, and may your dreams be as vast and wondrous as the universe itself. Our understanding of the cosmos has grown by leaps and bounds, but there's still so much more to discover. As we continue our journey through the wonders of deep space, let's turn our attention to some of the most fascinating and perplexing phenomena that astronomers have encountered in recent decades. One of the most mind-bending discoveries has been the existence of supermassive black holes lurking at the hearts of galaxies. These cosmic behemoths can contain millions or even billions of times the mass of our Sun, all compressed into a region smaller than our solar system. The immense gravity of these black holes can warp the fabric of space-time itself, creating bizarre effects that challenge our intuition. In the 1960s, astronomers began to detect intense sources of radio emission coming from the centres of some galaxies. They dubbed these objects quasars, short for quasi-stellar radio sources. At first, the nature of these bright beacons was a mystery. They appeared star-like, but their luminosities were hundreds of times greater than that of an entire galaxy. How could something so small shine so brightly? The answer lay in the extreme environment around supermassive black holes. As matter spirals inward toward the black hole, it forms a swirling disk called an accretion disk. Friction and gravitational stresses within the disk heat the material to incredible temperatures, causing it to blaze with the brightness of a trillion suns. Quasars are the most extreme examples of these active galactic nuclei, powered by the insatiable appetites of supermassive black holes. But black holes don't always devour matter so voraciously. In fact, most galaxies, including our own Milky Way, host quiescent supermassive black holes at their centres. These slumbering giants only occasionally feed, like cosmic bears awakening from hibernation. But when they do, they can produce some of the most dramatic displays in the universe. In 2019, astronomers captured the first direct image of gas swirling around the supermassive black hole at the centre of the galaxy M87. This remarkable feat was accomplished by linking radio telescopes around the world to create a virtual observatory the size of Earth itself. The resulting image showed a bright ring of light surrounding a dark region, the shadow cast by the black hole's event horizon, the point of no return beyond which nothing can escape. The M87 black hole is a monster, tipping the scales at over 6 billion times the mass of the Sun. But it's far from the only supermassive black hole out there. Astronomers now believe that virtually every large galaxy harbours one of these giants at its core. It seems that galaxies and their central black holes are intimately linked, though the exact nature of this relationship remains a mystery. Some of the most exciting black hole research today focuses on the gravitational waves produced when two black holes collide and merge. These ripples in the fabric of space-time, predicted by Albert Einstein's theory of general relativity, are so tiny by the time they reach Earth that detecting them is a monumental challenge. But in 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, did just that. ushering in a new era of astronomy. The gravitational waves detected by LIGO came from the merger of two stellar mass black holes, each about 30 times the mass of the Sun. As the black holes spiraled inward and collided, they radiated energy in the form of gravitational waves, sending tremors across the cosmos. LIGO's detection confirmed a key prediction of general relativity and opened a new window on the universe. Since that first detection, LIGO and its partner observatory Virgo have detected dozens more gravitational wave events, including the merger of two neutron stars, the ultra-dense remnants of massive stars that have exploded as supernovae. These cosmic collisions offer a glimpse into the most extreme environments in the universe and provide a new way to study the fundamental nature of gravity itself. As we ponder these discoveries, it's worth reflecting on the incredible progress astronomers have made in just a few short decades. In the span of a human lifetime, we've gone from wondering about the nature of quasars to imaging the shadow of a black hole, from theorizing about gravitational waves to detecting them directly. It's a testament to the power of human curiosity and the relentless pursuit of knowledge. And yet, for all that we've learned, there's still so much more to discover. What other exotic objects might be hiding in the depths of space, waiting to be found? Could there be entirely new types of celestial bodies that we haven't even conceived of yet? And what might we learn about the fundamental laws of nature by studying the extreme environments around black holes and neutron stars? These are the kinds of questions that keep astronomers awake at night, dreaming of the discoveries yet to come. And as we drift off to sleep ourselves, we can take comfort in the knowledge that, even as we slumber, telescopes around the world and in space are keeping a watchful eye on the cosmos, ready to catch the next great revelation from the depths of space. One of the most tantalizing prospects in modern astronomy is the search for planets around other stars, worlds beyond our own solar system. For centuries, philosophers and scientists alike have wondered whether the universe might be teeming with life, whether the conditions that gave rise to our own vibrant Earth might be replicated elsewhere in the cosmos. It wasn't until the 1990s that astronomers finally confirmed the existence of planets orbiting other stars. The first exoplanets, as they came to be known, were found around a pulsar, a rapidly spinning neutron star that emits beams of radiation like a cosmic lighthouse. But soon, astronomers began to find planets around more sun-like stars, using a variety of techniques. One of the most successful methods for finding exoplanets is the transit method. When a planet passes in front of its star from our point of view, it causes a tiny dip in the star's brightness, like a mosquito flying in front of a searchlight. By measuring these dips with exquisite precision, astronomers can not only detect the presence of a planet, but also measure its size and orbit. The Kepler Space Telescope, launched in 2009, used the transit method to survey a small patch of sky containing over 150,000 stars. Over the course of its 9-year mission, Kepler discovered more than 2,600 confirmed exoplanets, with thousands more candidates awaiting verification. The data from Kepler revealed that planets are astonishingly common in our galaxy, with virtually every star likely hosting at least one world. But Kepler did more than just count planets. It also gave us our first glimpse at the incredible diversity of worlds beyond our own solar system. Some of the planets discovered by Kepler are rocky worlds like Earth, while others are gas giants like Jupiter or Saturn. Some orbit so close to their stars that their surfaces are likely molten, while others follow wide, languid orbits in the cold depths of space. One of the most intriguing finds from Kepler was the discovery of super-Earths, planets larger than Earth but smaller than Neptune, with no direct analogue in our own solar system. These worlds blur the line between rocky planets and gas giants, and their discovery has forced astronomers to rethink their theories of planetary formation. Kepler also found planets orbiting in systems very different from our own, with multiple worlds packed into tight orbits around their stars. In some cases, these planetary systems seem to have formed in ways that challenge our understanding of how planets are born from the swirling disks of gas and dust around young stars. The success of Kepler paved the way for even more ambitious planet-hunting missions. The Transiting Exoplanet Survey Satellite, TS, launched in 2018, is scanning the entire sky for planets around nearby stars. TESS is expected to find thousands of new worlds, including many that are close enough for detailed study with other telescopes, and that detailed study is where the real excitement lies. Because once we know a planet exists, the next step is to try to learn more about its properties, its mass, its atmosphere, and ultimately whether it might be capable of supporting life. One of the most promising techniques for studying exoplanet atmospheres is called transmission spectroscopy. When a planet passes in front of its star, some of the starlight filters through the planet's atmosphere. By carefully analysing the spectrum of this filtered light, astronomers can detect the telltale signatures of different gases in the atmosphere, from familiar compounds like water vapour and carbon dioxide to more exotic substances like sodium and potassium. In the coming years, new telescopes like the James Webb Space Telescope and the European Extremely Large Telescope will use transmission spectroscopy and other techniques to study the atmospheres of potentially habitable worlds in unprecedented detail. They'll search for signs of water, methane, and other compounds that could indicate the presence of life. Of course, finding definitive evidence of life on another world is an enormous challenge. Even if we detect what looks like a biosignature in an exoplanet's atmosphere, it will take a lot of work to rule out non-biological explanations. And even if we do find compelling evidence of alien biology, it's likely to be microbial life rather than the kind of complex organisms we see on Earth. But the possibility is tantalizing nonetheless. The idea that we might one day discover that we're not alone in the universe, that life has taken root on worlds beyond our own, is one of the most profound and exciting prospects in all of science. And as we drift off to sleep, our minds can wander to those distant worlds, imagining what strange and wonderful forms life might take under alien suns. Perhaps there are creatures swimming in the subsurface oceans of icy moons, or floating in the cloud tops of gas giants. Perhaps there are civilizations rise and fall on the worlds of faraway stars, grappling with the same questions and challenges that we face here on Earth. The search for life beyond Earth is ultimately a search for our own place in the cosmos. It's a way of asking whether the processes that gave rise to us are universal, or whether we're a rare and precious outlier in a vast and largely sterile universe. It's a way of exploring the very nature of life itself, and the myriad ways in which it might manifest across the incredible diversity of worlds in our galaxy and beyond. And so, as we close our eyes and let sleep take us, we can dream of those other worlds and the countless possibilities they represent. We can take comfort in the knowledge that, even as we slumber, the great cosmic dance of planets and stars continues, a testament to the endless creativity and complexity of the universe we call home. The wonders of the cosmos are not limited to the planets and stars we can see with our telescopes. Some of the most fascinating and mysterious phenomena in the universe are the ones we can't see at all, the invisible components that make up the vast majority of the cosmos. One of these invisible components is dark matter. Astronomers have known for decades that the galaxies and clusters we observe are far more massive than can be accounted for by the visible matter alone. The stars, gas, and dust that we can see make up only a small fraction of the total mass. The rest is a form of matter that doesn't interact with light at all, rendering it invisible to our telescopes. The evidence for dark matter comes from a variety of observations. We see its gravitational influence in the way galaxies rotate, in the way light from distant galaxies is distorted as it passes through massive clusters, and in the intricate patterns of the cosmic microwave background. All of these observations point to the same conclusion. There is far more matter in the universe than meets the eye. But what exactly is dark matter? That remains one of the greatest unsolved mysteries in modern physics. Theorists have proposed a wide range of possibilities, from exotic new particles like axions and sterile neutrinos to primordial black holes and even modified theories of gravity. But so far, none of these ideas have been confirmed by experiment. The search for dark matter is one of the most active areas of research in physics today. Experiments deep underground are searching for the telltale signals of dark matter, particles colliding with ordinary atoms. Particle colliders are trying to produce dark matter in the lab, and astrophysicists are studying the behaviour of galaxies and clusters in ever greater detail, looking for clues to the nature of this elusive substance. But dark matter is only part of the story. In the late 1990s, astronomers made another startling discovery. The expansion of the universe is accelerating. This finding came from observations of distant supernovae, which revealed that the universe is not only expanding, but that the expansion is speeding up over time. This discovery was completely unexpected. Most astronomers had assumed that the gravitational pull of matter would slow the expansion of the universe over time, eventually bringing it to a halt or even reversing it. The fact that the expansion is actually accelerating suggests that there is some kind of energy permeating the cosmos, counteracting the pull of gravity on the larger scales. This mysterious energy has been dubbed dark energy, and it's even more perplexing than dark matter. Unlike dark matter, which clusters around galaxies and clusters, dark energy seems to be spread evenly throughout space. And while dark matter interacts with ordinary matter through gravity, dark energy appears to interact with nothing at all. It's a pure energy field that exists independently of matter. The nature of dark energy is one of the deepest puzzles in modern cosmology. Some theorists have suggested that it might be a manifestation of the vacuum energy predicted by quantum mechanics, the intrinsic energy of empty space itself. Others have proposed that it could be a new kind of dynamical field, similar to the fields that give rise to the fundamental forces of nature. Still others have argued that it might be a sign that our understanding of gravity is incomplete, and that we need a new theory to explain the behavior of the universe on the larger scales. Regardless of its ultimate nature, the discovery of dark energy has profound implications for the fate of the universe. If dark energy continues to dominate the expansion of the cosmos, as seems likely, then the universe will keep expanding faster and faster, eventually tearing itself apart in a big rip. Galaxies will be separated from each other by vast stretches of empty space, stars will be ripped from their galaxies, and even atoms will be torn asunder as the fabric of space itself stretches beyond the breaking point. It's a sobering thought to contemplate the ultimate fate of the cosmos, but it's also a reminder of the incredible scope and scale of the universe we inhabit. From the tiniest subatomic particles to the grandest structures of the cosmos, from the birth of the first stars to the death throes of the last galaxies, the story of the universe is one of unending change and transformation. And as we lie here in the darkness, our minds drifting towards sleep, we can take solace in the knowledge that we are a part of that story. The atoms that make up our bodies were forged in the hearts of long-dead stars scattered across the cosmos by ancient supernovae. We are stardust, born of the universe's endless cycle of creation and destruction. And though our individual lives may be fleeting, the quest to understand the cosmos is a legacy that endures across generations. From the first humans who looked up at the night sky in wonder, to the astronomers and physicists who probe the deepest mysteries of the universe today, the story of our species is intertwined with the story of the cosmos itself. So let us dream of dark matter and dark energy, of distant galaxies and alien worlds, of the birth and death of the universe itself. Let us be humbled by the vastness of the cosmos and the depths of our ignorance, but also inspired by the incredible progress we've made in unravelling its secrets. And let us never lose sight of the fact that, for all the wonders of the universe beyond our world, the greatest miracle of all is the fact that we're here to ponder it, to study it, and to be a part of its grand unfolding. As we surrender to sleep, we can take comfort in the knowledge that the cosmos will be there when we wake, as it has been for billions of years and will be for billions more. And though we may be small and fleeting in the grand scheme of things, we are also a vital part of the universe's great story, a story of discovery, of wonder, and of the unending quest to understand our place in the grand tapestry of existence. As we continue our journey through the cosmos, we find ourselves drawn to some of the most enigmatic and awe-inspiring structures known to science: black holes. These gravitational behemoths have captured our imagination for decades, yet they remain shrouded in mystery. The story of black holes begins, as many scientific tales do, with the brilliant mind of Albert Einstein. In 1915, Einstein unveiled his groundbreaking theory of general relativity, which redefined our understanding of gravity. According to Einstein, gravity is not merely a force, but a warping of the very fabric of space and time. Massive objects like stars and planets create depressions in this cosmic fabric, like bowling balls resting on a trampoline. Smaller objects like moons and asteroids follow these curved paths, orbiting the larger masses. But Einstein's equations held a surprising implication. If an object became sufficiently dense, its gravity could warp space so severely that not even light could escape its grasp. This bizarre idea seemed like a mere mathematical curiosity at first, but as astronomers peered deeper into the universe, they began to suspect that such objects might actually exist. In 1916, barely a year after Einstein published his theory, German physicist Karl Schwarzschild derived a solution to Einstein's equations that described the gravitational field of a point mass. This mathematical description suggested that if a star collapsed to a single point, its density would become infinite, and it would create an inescapable gravitational vortex, a black hole. At the time, the notion seemed purely theoretical, a quirk of the equations rather than a real cosmic possibility. However, in the late 1960s, a young physicist named John Wheeler began to take the idea of collapsed stars more seriously. Wheeler, known for his colourful language and vivid imagination, coined the term black hole to describe these gravitational monsters. The name captured the public's imagination and sparked a wave of interest in these mysterious objects. But how could astronomers possibly detect a black hole, an object so dense that it swallows light itself? The answer lies not in the black hole itself, but in its effects on the surrounding space. As matter spirals towards a black hole, it accelerates to tremendous speeds, forming a swirling disk called an accretion disk. Friction within this disk causes it to heat up to incredible temperatures, emitting X-rays that we can detect with specialized telescopes. In 1964, Cygnus X1 became the first candidate for a black hole ever observed. This X-ray source, located within our own Milky Way galaxy, emitted X-rays so powerful that astronomers suspected it must be caused by matter falling into a black hole. Further observations revealed that Cygnus X1 was actually part of a binary star system, with a visible star orbiting an unseen companion, likely a black hole several times more massive than our Sun. Over the following decades, astronomers discovered many more of these X-ray binaries, each one a potential black hole devouring its companion star. But these stellar mass black holes, formed from the collapse of individual stars, are mere cosmic minnows compared to the behemoths lurking at the hearts of galaxies. In the 1970s, astronomers using radio telescopes discovered strange, compact sources of radio waves at the centres of some galaxies. These sources, dubbed quasars, were incredibly bright, outshining entire galaxies despite being no larger than our solar system. The only way to explain such tremendous energy output from such a small region was to invoke the power of supermassive black holes, millions or even billions of times more massive than our Sun. As we now know, these supermassive black holes reside at the centre of nearly every large galaxy, including our own Milky Way. In the 1990s, observations of stars orbiting the galactic centre revealed the presence of an invisible object some 4 million times more massive than the Sun, confined to a region smaller than our solar system. This object, known as Sagittarius A star, is the supermassive black hole anchoring our galaxy. But how did these cosmic monsters grow so large? Astronomers believe that supermassive black holes likely began as smaller, seed black holes in the early universe, perhaps formed from the very first generation of stars. Over billions of years, these seeds merged and grew as their host galaxies collided and coalesced, feeding on gas, dust, and unfortunate stars that ventured too close. In 2019, the Event Horizon Telescope collaboration achieved a landmark in black hole astronomy, the first direct image of a black hole's event horizon, the point of no return beyond which even light cannot escape. This remarkable image, resembling a glowing orange donut, captured the supermassive black hole at the heart of the galaxy Messier 87, some 55 million light-years away. The bright ring is the accretion disk, heated to incandescence as it swirls around the black hole's event horizon, the dark central void from which no light can emerge. This image, the product of years of international collaboration and cutting-edge technology, opened a new window onto these extreme cosmic objects. Yet it also underscored the many mysteries that remain. What happens to matter that falls into a black hole? Is there a singularity at the centre, a point where the laws of physics break down? And what can black holes tell us about the fundamental nature of space, time, and gravity? As we ponder these questions, we find ourselves once again humbled by the vastness and complexity of the universe. Black holes, once mere mathematical curiosities, have become central to our understanding of the cosmos. They are not merely cosmic oddities, but key players in the growth and evolution of galaxies, shaping the very structure of the universe on the grandest scales. And so, as we drift off to sleep, let us dream of these enigmatic giants, their gravity so immense that they warp the very fabric of reality. In our mind's eye, we can picture the glowing accretion disks, the jets of energetic particles shooting into space, and the dark, inscrutable event horizons that mark the boundary between the known and the unknowable. The story of black holes reminds us that the universe is a place of endless wonder and mystery, forever beckoning us to explore its darkest corners and most brilliant horizons. Good night, and may your dreams be filled with the beauty and grandeur of the cosmic dance. As our minds continue to wander through the vast expanse of the universe, we find ourselves drawn to another cosmic mystery: dark matter. This invisible substance, which makes up over 80% of the matter in the universe, has eluded our direct detection for decades. Yet its gravitational influence can be seen everywhere we look, from the motions of stars within galaxies to the large-scale structure of the cosmos itself. The story of dark matter begins in the 1930s with the work of Swiss-American astronomer Fritz Zwicky. While studying the Coma Cluster, a vast collection of over 1,000 galaxies some 320 million light-years away, Zwicky noticed something peculiar. The galaxies within the cluster were moving far too quickly relative to one another. Based on the visible matter alone, the cluster should have long since flown apart. Zwicky concluded that there must be some unseen matter holding the cluster together, a dark matter exerting a gravitational pull on the galaxies. At the time, Zwicky's idea was met with skepticism. Many astronomers believed that the discrepancy could be explained by ordinary matter that was simply too faint to detect, such as cool gas or dim stars. But as observations improved over the following decades, the evidence for dark matter began to mount. In the 1970s, American astronomer Vera Rubin provided some of the most compelling evidence for dark matter to date. Rubin and her colleague Kent Ford studied the rotation curves of spiral galaxies, measuring how quickly stars orbited the galactic center at different distances. According to Newton's laws of gravity, stars far from the galactic center, where most of the visible matter is concentrated, should orbit more slowly than stars closer in. But Rubin and Ford found that the stars' orbital speeds remained remarkably constant with distance, implying that the galaxies contained far more mass than could be accounted for by visible matter alone. This flat rotation curve problem, as it came to be known, was not unique to the galaxies Rubin and Ford studied. As more and more spiral galaxies were observed, the same pattern emerged time and time again. The inescapable conclusion was that galaxies were embedded within vast halos of invisible matter, extending far beyond the visible stars and gas. But what is this dark matter exactly? Despite decades of searching, we still don't know for sure. One leading candidate is a type of particle called a WIMP, or weakly interacting massive particle. As the name suggests, these hypothetical particles would have a large mass but rarely interact with ordinary matter, making them exceedingly difficult to detect. Scientists around the world have built elaborate underground detectors, shielded from cosmic radiation and other background noise, in hopes of catching a fleeting interaction between a WIMP and an atomic nucleus. So far, these experiments have come up empty, but the search continues, with ever more sensitive detectors coming online in the hopes of finally pinning down this elusive particle. Another approach to the dark matter problem has been to look for its gravitational effects on a cosmic scale. In the late 1990s, astronomers used the Hubble Space Telescope to study the most distant supernova ever observed. These exploding stars, billions of light years away, can be used as standard candles to measure the expansion of the universe. To their surprise, the astronomers found that the expansion was actually accelerating, driven by a mysterious dark energy that counteracts the pull of gravity on cosmic scales. Further studies of the cosmic microwave background, the leftover radiation from the Big Bang, have revealed the large-scale distribution of matter in the early universe. These studies show that the universe is made up of about 5% ordinary matter, 27% dark matter, and 68% dark energy. In other words, the stuff we can see, stars, planets, galaxies, is just a tiny fraction of what's actually out there. The discovery of dark matter and dark energy has thrown a wrench into our understanding of the cosmos. These mysterious substances don't fit neatly into the standard model of particle physics, our best description of the subatomic world. Some theorists have proposed modifications to gravity itself, such as the theory of modified Newtonian dynamics and MOND, to explain the observed effects without invoking new forms of matter. But so far, dark matter remains the most successful explanation for a wide range of astronomical observations. As we lie here in the darkness, our minds drift to the unseen matter that surrounds us. In our mind's eye, we can picture the vast invisible halos enveloping galaxies, the cosmic web of dark matter, filaments stretching between them, and the bubbles of dark energy pushing everything apart. We are reminded that our universe is stranger and more wonderful than we ever could have imagined, full of mysteries waiting to be unravelled. Perhaps someday, a lucky scientist will finally detect a WIMP in an underground lab, or a new theory will emerge to explain the cosmos without the need for dark matter. Until then, we can only marvel at the incredible progress we've made in understanding our universe and dream of the discoveries yet to come. As we slip into a peaceful slumber, let us carry with us a sense of awe and wonder at the grand cosmic dance playing out on scales beyond our imagining, a silent symphony of dark matter and dark energy, guiding the evolution of galaxies and the fate of the universe itself. As we continue our journey through the wonders of deep space, we find ourselves drawn to the most mysterious and mind-bending objects in the cosmos: black holes. These cosmic behemoths are so dense that not even light can escape their grasp, making them invisible to our telescopes. Yet, we know they exist, lurking in the hearts of galaxies and the remnants of collapsed stars. The story of black holes begins with the work of physicists in the early 20th century. In 1916, just after Albert Einstein published his groundbreaking theory of general relativity, German physicist Karl Schwarzschild derived a solution to Einstein's equations that described a bizarre object, a point in space with infinite density, surrounded by an event horizon, a boundary beyond which nothing, not even light, could escape. These strange theoretical objects came to be known as black holes. For decades, black holes remained in the realm of mathematical curiosities. Many scientists, including Einstein himself, doubted whether such extreme objects could actually exist in nature. But as astronomical observations improved, hints of their presence began to emerge. In the 1960s, astronomers discovered distant objects called quasars that shone with the brilliance of hundreds of galaxies, yet were no larger than our solar system. What could power such incredible luminosity from such a compact region? The answer, it turned out, was a supermassive black hole, millions or even billions of times the mass of our Sun, feeding on a swirling disk of gas and dust. Close to home, astronomers studying the motion of stars in the heart of our own Milky Way galaxy found evidence for an invisible mass 4 million times that of the Sun, all concentrated in a region smaller than our solar system. This too was likely a supermassive black hole lurking at the centre of our galactic home. Black holes, it seemed, were not just theoretical constructs but real objects woven into the fabric of the universe itself. But how did they form? And what would happen to an object unfortunate enough to fall into one? The answers lie in the death throes of massive stars. Stars are held in a delicate balance, with the inward crush of gravity counteracted by the outward pressure of nuclear fusion in their cores. But for stars more than a few times the mass of our Sun, this balance is ultimately doomed. When such a star exhausts its nuclear fuel, its core collapses under its own immense gravity, triggering a cataclysmic supernova explosion. The outer layers of the star are blasted into space, but if the collapsing core is massive enough, nothing can stop its inward plunge. It collapses all the way down to an infinitesimal point, and a black hole is born. So what would happen if you fell into one of these cosmic sinkholes? According to Einstein's theory, as you approach the black hole, you would begin to feel the increasing tidal forces of gravity. If the black hole was a stellar mass one the size of a city, these forces would be gentle at first, but as you drew near the event horizon, they would intensify enormously. The force on your feet would be so much stronger than the force on your head that you would be stretched vertically and compressed horizontally in a process whimsically called spaghettification. As you crossed the event horizon, you would pass the point of no return. Even if you fired rockets, you could never escape the black hole's gravitational grip. From the perspective of a distant observer, you would appear to slow down as you approach the event horizon, your image becoming increasingly redshifted until you faded from view entirely. But from your own perspective, you would speed across the boundary in finite time. What would you find inside? That's where our current theories break down. At the centre of a black hole lies a singularity, a point where the known laws of physics crumble in the face of infinite density and zero volume. It's a realm where our understanding reaches its limit, where space and time as we know them cease to exist. Some physicists theorize that a singularity might be a gateway to another universe, or perhaps a transitional state in an endlessly cycling cosmos. But for now, the true nature of singularities remains one of the deepest mysteries in science. Black holes, however, are not just isolated objects. They can have profound effects on their surroundings. As matter spirals into a black hole, it forms an accretion disk where it becomes superheated and emits copious amounts of radiation before making its final plunge. Some of this infalling matter can also be redirected, blasting outward in colossal jets at nearly the speed of light. These jets can extend for hundreds of thousands of light years, far beyond the galaxy hosting the black hole. In recent years, astronomers have begun to directly observe the immediate environs of black holes using very long baseline interferometry, a technique that links radio telescopes around the world to form one giant Earth-sized observatory. In 2019, the Event Horizon Telescope collaboration released the first ever direct image of a black hole, the supermassive behemoth at the heart of the galaxy M87. The image shows a dark central region surrounded by a bright ring of light, bent by the immense gravity into the shape of the black hole's shadow. It was a stunning confirmation of predictions made by Einstein's theory a century earlier. As you drift off, your mind might wander to the black holes scattered throughout the cosmos, from the stellar mass ones born in the deaths of stars to the supermassive ones lurking at the hearts of galaxies. Each one is a portal to the unknown, a reminder of how much we still have to learn about the universe we call home. And as you slip into the realm of dreams, you might imagine yourself on a cosmic journey, falling through the event horizon, ready to discover what lies beyond our current understanding in the uncharted depths of a black hole. But black holes are not the only strange and wonderful objects populating the depths of space. Out there, among the stars, are worlds very different from our own, planets that stretch our imagination and redefine what we think of as possible. Not so long ago, the only planets we knew of were the ones in our own solar system. But in the last few decades, a revolution has taken place in astronomy. Advances in telescope technology have allowed us to detect planets orbiting other stars, exoplanets. And what we've found has been nothing short of astonishing. The first exoplanet was discovered in 1992, orbiting a pulsar, the rapidly spinning remnant of a massive star that had exploded as a supernova. This planet, and a few others found orbiting pulsars in the following years, had presumably formed after the supernova from the debris left behind. They hinted at the resilience of planetary formation, but they were very different from the planets in our solar system. The real breakthrough came in 1995, with the discovery of the first exoplanet orbiting a Sun-like star. This planet, 51 Pegasi b, was about half the mass of Jupiter, but it orbited its star at a distance closer than Mercury orbits the Sun. It was a hot Jupiter, a gas giant so close to its star that its atmosphere is bloated and blasted by stellar radiation. As more and more exoplanets were discovered, astronomers realized that our solar system might be more the exception than the rule. Many star systems, it seemed, were home to these hot Jupiters, gas giants that had migrated inward from their birth orbits to bask in the heat of their stars. But as detection methods improved, astronomers began to find smaller, rockier worlds as well. Some of these were super-Earths, planets a few times the mass of our own world, and some were even more intriguing, planets that orbited in their stars' habitable zones, the range of distances where temperatures could allow for liquid water on a planet's surface. The possibility of liquid water raises tantalizing questions about the potential for life on these worlds. On Earth, wherever we find liquid water, we find life. Could the same be true on planets orbiting other stars? To answer this question, astronomers are developing new technologies to study the atmospheres of exoplanets. When a planet passes in front of its star, a tiny fraction of the starlight filters through the planet's atmosphere. By studying the spectrum of this light, astronomers can look for the chemical signatures of life, such as oxygen, ozone, and methane. In the coming years, powerful new telescopes, both on the ground and in space, will begin to search for these biosignatures. The James Webb Space Telescope, launched in 2021, will be able to detect the infrared glow of exoplanets and study their atmospheres in unprecedented detail, and future missions like the proposed LUVOIR Space Telescope could even image Earth-like exoplanets directly, allowing us to see oceans, continents, and perhaps even the glint of alien cities. As you let your mind drift among these distant worlds, imagine the countless possibilities they represent. On how many of them has the spark of life taken hold? Are there intelligent beings out there, looking up at their own night skies, wondering if they're alone in the universe? Perhaps someday we'll know the answer. And so, as you slip into the realm of dreams, keep these wonders close to your heart. The universe is vast beyond our imagining, filled with mysteries and marvels that we're only just beginning to uncover. From the black holes spinning in the hearts of galaxies to the exoplanets orbiting distant stars, each new discovery opens up new horizons, new possibilities for exploration and understanding. Perhaps, as you dream, you'll find yourself walking beneath alien skies, on worlds yet to be discovered. Or perhaps you'll dive into the heart of a black hole, ready to unravel the secrets of the cosmos. Whatever visions come to you in the night, hold on to the sense of wonder that the universe inspires in us all. Because that's what drives us to keep exploring, to keep asking questions and seeking answers. It's what's led us from the first stargazers charting the motions of the heavens to the astronomers of today peering billions of light years into space, and it's what will lead us, in the years and centuries to come, to new revelations, new understanding, and new appreciation for the incredible cosmos we call home. So as you drift off to sleep, let your dreams be filled with the wonders of the universe. Let them inspire you, as they've inspired countless others before you, to keep looking up, keep asking questions, and keep marveling at the incredible, endlessly fascinating depths of space. Good night, and sweet dreams of the cosmos. As we continue our journey through the cosmos, let's turn our attention to some of the most enigmatic objects in the universe, black holes. These bizarre entities are so dense that not even light can escape their powerful gravitational pull. The idea of an object so massive that it could trap light was first proposed in the late 18th century by the English geologist John Michel and the French mathematician Pierre-Simon Laplace. However, their insights were largely forgotten until the 20th century, when Albert Einstein's revolutionary theory of general relativity provided a theoretical framework for understanding these extreme concentrations of mass. Einstein's equations suggested that if a sufficiently massive star exhausted its nuclear fuel and collapsed under its own gravity, it could form a black hole. But for many years, these objects remained purely theoretical constructs. It wasn't until the 1960s that astronomers found the first observational evidence for their existence. In 1964, Jocelyn Bell Burnell, a young graduate student at Cambridge University, was analysing data from a new radio telescope. She noticed a strange signal, a regular pulse of radio waves, repeating every 1.33 seconds with clockwork precision. At first, Bell Burnell and her supervisor, Anthony Hewish, jokingly nicknamed the signal LGM-1 for Little Green Men, wondering if they had detected a beacon from an alien civilization. However, as they found more examples of these pulsating radio sources, they realized they had discovered something entirely new: rapidly spinning neutron stars, or pulsars. Neutron stars are the ultra-dense remnants of massive stars that have exploded as supernovae. They pack the mass of the Sun into a sphere only about 20 kilometers across, making them so dense that a teaspoon of neutron star material would weigh about 1 billion tons on Earth. When these objects spin, they emit beams of radio waves from their magnetic poles, which sweep across space like cosmic lighthouses. If one of these beams happens to point towards Earth, we observe regular pulses of radio emission each time the beam rotates into our line of sight. The discovery of pulsars was a major breakthrough, providing the first observational evidence for the existence of neutron stars. But pulsars were just the beginning. As astronomers continued to probe the depths of space with new and more powerful telescopes, they uncovered even stranger phenomena that hinted at the presence of black holes. In the 1960s, astronomers began to detect strong X-ray sources from various locations in the sky. The first of these cosmic X-ray beacons to be discovered was Cygnus X1, located in the constellation of Cygnus the Swan. Further observations revealed that Cygnus X1 was actually two objects, a massive blue star and an invisible companion, locked in a tight orbital dance. The X-rays, astronomers realized, must be generated by matter from the visible star falling towards the invisible one. But what was the nature of this dark companion? Calculations showed that it was far too massive to be a white dwarf or a neutron star. The only remaining possibility was a black hole. As matter spirals towards a black hole, it forms a swirling disk called an accretion disk. Friction and gravitational stresses in the disk heat the material to extreme temperatures, causing it to emit X-rays. This finally explained the intense X-ray glow of Cygnus X1 and similar systems. Over the following decades, astronomers discovered many other black hole candidates in X-ray binary systems throughout the Milky Way. But these were all relatively small black holes, a few times the mass of the Sun. Even more astounding discoveries were yet to come. In the 1980s, astronomers began to realize that the centers of many galaxies, including our own Milky Way, harbored much more massive black holes, millions or even billions of times the mass of the Sun. The first compelling evidence for these supermassive black holes came from observations of the galaxy Messier 87, located about 55 million light-years from Earth in the constellation Virgo. In 1978, astronomer Peter Young and his colleagues used a sensitive new camera to measure the velocities of stars and gas clouds near the center of M87. To their surprise, they found material whirling around the galactic center at astonishing speeds, some approaching 1.5 million miles per hour. The only way to explain such extreme velocities was the presence of a tremendous concentration of mass at the galaxy's heart, something with the mass of about 3 billion suns, confined to a region smaller than our solar system. Over the following years, observations of other galaxies revealed similar evidence for supermassive black holes at their centers. Even our own Milky Way, it turned out, harbors a black hole with a mass of about 4 million suns at its core. Astronomers called this object Sagittarius a star, and it soon became one of the most intensely studied objects in the sky. But how did these behemoths form, and what role do they play in the evolution of galaxies? These questions remain active areas of research today. One leading theory suggests that supermassive black holes may have formed from the collapse of giant gas clouds in the early universe, shortly after the Big Bang. Over billions of years, these seed black holes grew by pulling in gas and dust, and by merging with other black holes during galactic collisions. As they feed, supermassive black holes can unleash enormous amounts of energy. Material swirling into the black hole can become so hot and bright that it outshines the entire host galaxy, creating a quasar. The intense radiation and particle jets from quasars can influence star formation and gas dynamics throughout the galaxy, shaping its evolution over cosmic timescales. Despite their importance, black holes remained one of the most mysterious objects in the universe for decades. By their very nature, they are invisible, detectable only through their effects on nearby matter and light. But in 2019, astronomers finally captured the first direct image of a black hole using a global network of radio telescopes called the Event Horizon Telescope. The target of this historic observation was the supermassive black hole at the center of Messier 87, the same galaxy studied by Peter Young and his colleagues 4 decades earlier. The resulting image, which made headlines around the world, showed a bright ring of light surrounding a dark central region. The black hole's event horizon, the point of no return beyond which nothing, not even light, can escape. This remarkable achievement marked the beginning of a new era in the study of black holes. By directly imaging the event horizons of these extreme objects, astronomers hope to test the predictions of Einstein's theory of general relativity in the strong gravity regime, and to learn more about the role of supermassive black holes in the formation and evolution of galaxies. As we ponder these cosmic mysteries, it's worth reflecting on the incredible progress we've made in our understanding of the universe. In just a few centuries, we've gone from wondering about the nature of the fixed stars to imaging the event horizons of black holes billions of light-years away. Each new discovery has expanded our cosmic horizons and deepened our appreciation for the astonishing variety and beauty of the cosmos. And yet, for all we've learned, there is still so much we don't know. What other exotic objects and phenomena await discovery in the uncharted depths of space? What will the next generation of telescopes and space missions reveal about the nature of reality? As we drift off to sleep, let's allow our dreams to carry us to the frontiers of cosmic exploration, inspired by the wonders we've uncovered and the mysteries that remain. Perhaps one of the greatest remaining mysteries is the nature of dark matter and dark energy. These invisible components make up about 95% of the universe, yet we still don't know what they are. Dark matter, first proposed in the 1930s by astronomer Fritz Zwicky, is a form of matter that doesn't interact with light, making it invisible to our telescopes. However, we can detect its presence through its gravitational effects on visible matter. In the 1970s, astronomer Vera Rubin provided strong evidence for dark matter when she studied the rotation curves of galaxies. She found that stars and gas at the outer edges of galaxies were moving much faster than expected based on the amount of visible matter. The only way to explain these motions was if galaxies were embedded in large halos of unseen matter, dark matter. Subsequent observations have confirmed the presence of dark matter on cosmic scales. Gravitational lensing studies, which observe how the gravity of massive objects bends the path of light from distant sources, have revealed vast webs of dark matter connecting and surrounding galaxies and galaxy clusters. The cosmic microwave background, the afterglow of the Big Bang, also bears the imprints of dark matter in the early universe. Despite its pervasiveness, the nature of dark matter remains elusive. Is it made of undiscovered subatomic particles, such as hypothetical weakly interacting massive particles, WIMPs, or could it be something even more exotic, like primordial black holes or cosmic strings? Experiments around the world are currently searching for signs of dark matter particles, but so far the search has come up empty. Even more mysterious is dark energy, a form of energy that seems to permeate all of space and is causing the expansion of the universe to accelerate. The first evidence for dark energy came in the late 1990s when two teams of astronomers were using distant exploding stars called Type Ia supernovae to measure the expansion rate of the universe. To their surprise, they found that the universe is not only expanding, but its expansion is speeding up over time. This discovery sent shockwaves through the astronomical community. The only way to explain this accelerating expansion was if space itself possessed a sort of intrinsic energy, dark energy, that counteracts the pull of gravity on cosmic scales. Subsequent observations, including detailed measurements of the cosmic microwave background and large-scale galaxy surveys, have confirmed the existence of dark energy. But like dark matter, its fundamental nature remains a mystery. Is it a constant energy density that fills all of space, as suggested by Einstein's cosmological constant? Or could it be something more dynamic, like a new type of field that evolves over cosmic time? These questions lie at the forefront of cosmological research today. Upcoming experiments such as the Vera C. Rubin Observatory and the Euclid Space Telescope will map billions of galaxies across vast swaths of the sky, seeking to unravel the mysteries of dark matter and dark energy. By studying how these components have shaped the growth of cosmic structure over billions of years, astronomers hope to gain insight into their fundamental nature. As we contemplate these profound mysteries at the heart of the cosmos, it's humbling to consider how much we've learned and how much we still have yet to discover. In a sense, we are like the ancient stargazers who looked up at the night sky and wondered about the nature of the celestial lights. But armed with the tools and knowledge of modern science, we can peer deeper into the cosmos than ever before, seeking answers to age-old questions about the nature of reality and our place within it. And so, as we prepare to drift off into the realm of dreams, let's carry with us a sense of wonder and curiosity about the universe we inhabit. From the nearest stars to the most distant galaxies, from the tiniest subatomic particles to the vast cosmic web, the cosmos is filled with marvels waiting to be explored. May our dreams be filled with the beauty and mystery of the universe, inspiring us to continue the great human quest to understand our cosmic home. The cosmic mysteries we've unraveled so far are but a prelude to the discoveries that await us in the future. As we continue to probe the depths of space with ever more sophisticated tools, we stand poised to answer some of the most profound questions about the universe and our place within it. One of the most tantalizing enigmas is the nature of dark matter and dark energy. These invisible components make up the vast majority of the universe, yet their true identities remain elusive. Dark matter, first proposed in the 1930s by Fritz Zwicky, exerts a gravitational pull on visible matter, but does not interact with light. It helps explain the rotational speeds of galaxies and the motions of galaxies within clusters. Without it, galaxies would fly apart like an untethered carousel. Dark energy, discovered in the late 1990s, is an even more baffling entity that permeates all of space and causes the expansion of the universe to accelerate. It is the cosmic fuel that propels galaxies away from each other at ever-increasing speeds. Together, dark matter and dark energy are the hidden puppeteers that shape the structure and fate of the cosmos. To unravel these mysteries, astronomers are employing a range of innovative techniques. Gravitational lensing, where the gravity of massive objects bends and distorts the light from more distant sources, allows us to map the distribution of dark matter in the universe. By studying how light from far-flung galaxies is warped and stretched as it passes through intervening dark matter, we can create a cosmic cartography of the unseen. Meanwhile, ever larger galaxy surveys aim to chart the growth of cosmic structure over time, tracing how dark matter and dark energy have sculpted the universe from its earliest epochs to the present day. Like forensic detectives piecing together clues, astronomers are slowly assembling a portrait of the dark side of the cosmos. As we gaze deeper into space, we also look further back in time. The finite speed of light means that the most distant objects we observe are also the oldest, their photons having journeyed for billions of years to reach our telescopes. By studying the most ancient galaxies and quasars, we can witness the universe in its infancy, when the first stars and galaxies were just beginning to blaze forth from the cosmic dawn. The James Webb Space Telescope, launched in 2021, is peering back to this formative era, when the universe was a mere fraction of its current age. Its infrared eyes are sensitive to the faint red-shifted glow of these primordial structures, allowing us to study how the first generation of stars and galaxies formed and evolved. Like cosmic archaeologists sifting through the earliest layers of creation, we are uncovering the building blocks that gave rise to the universe we inhabit today. Even as we push the boundaries of the observable universe, we are also discovering new worlds closer to home. The last few decades have witnessed a revolution in our understanding of planets beyond our solar system. In 1992, astronomers Alexander Wolszczan and Dale Frail discovered the first exoplanets orbiting a pulsar, a rapidly spinning neutron star. Since then, the floodgates have opened, with thousands of exoplanets now known, ranging from searing hot Jupiters skimming the surfaces of their stars to frigid, rocky worlds orbiting in the deep freeze far beyond their star's warmth. We've found planets circling binary stars, planets with multiple suns in their skies, and even rogue planets drifting alone through the interstellar void. The sheer diversity of worlds out there is astounding, challenging our preconceptions of what a planetary system can be. Among this menagerie of worlds, some may harbour the greatest prize of all, life itself. The search for biosignatures, such as atmospheric gases that could be produced by living organisms, is one of the most exciting frontiers in astronomy today. Telescopes like the European Extremely Large Telescope, currently under construction in the Chilean Andes, will have the capability to directly image Earth-like planets around nearby stars and study their atmospheres for hints of life. Meanwhile, the Transiting Exoplanet Survey satellite TESS is scanning the skies for rocky worlds orbiting in the habitable zones of their stars, where liquid water could potentially exist on their surfaces. Each new world we discover brings us one step closer to answering the age-old question, are we alone in the universe? As we ponder these profound questions, we must also reckon with the vast gulfs of space and time that separate us from the stars. The nearest star system to Earth, Alpha Centauri, lies just over 4 light-years away, a distance that would take our fastest spacecraft tens of thousands of years to traverse. The most distant galaxies we've observed so far are over 13 billion light-years away, their light having set out on its cosmic journey when the universe was still in its infancy. The sheer scale of the universe is humbling, reminding us of our own cosmic insignificance. Yet, in a very real sense, we are the universe's way of knowing itself. The atoms that make up our bodies were forged in the crucibles of ancient stars, scattered across the cosmos in their dying breaths. We are stardust given form and consciousness, the universe made manifest. Through our telescopes and space probes, we are the eyes and ears of the cosmos, the means by which it can marvel at its own grandeur. In studying the universe, we are ultimately studying ourselves, our origins, our place in the grand tapestry of existence, and our ultimate fate. As we drift off to sleep, let us dream of the wonders that still lie undiscovered in the depths of space. May we awaken to a universe that is every bit as beautiful, mysterious, and awe-inspiring as the one we have come to know through the tireless efforts of generations of astronomers and scientists. and may we never lose sight of the profound privilege it is to be a part of this cosmic story, to gaze upon the stars and to ponder the mysteries of the universe that cradles us. In the end, we're all just temporary guests in this grand cosmic palace, but through our boundless curiosity and ceaseless exploration, we can leave a lasting legacy, a species that dared to reach for the stars and in so doing, came to know the universe and its place within it just a little bit better. Sweet dreams, fellow traveller, and may the cosmos be your guide. As we ponder the vast expanse of the universe, it's humbling to realise that our cosmic story is still unfolding, page by page, as we continue to explore and discover. The Hubble Space Telescope, a marvel of human ingenuity, has been our faithful guide on this journey, but it is not the only intrepid explorer of the cosmos. In 2009, NASA launched the Kepler Space Telescope with a singular mission: to search for planets orbiting other stars. Kepler stared at a patch of sky in the constellation Cygnus, watching and waiting for the telltale flicker of a planet passing in front of its host star. With unwavering patience, Kepler monitored the light of over 150,000 stars, seeking these tiny dips in brightness. And what a bountiful harvest of worlds it found. Within just a few years, Kepler had discovered thousands of exoplanets, alien worlds orbiting distant suns. Some were familiar, gas giants, and rocky worlds not unlike those in our own solar system. But others were utterly alien, planets that orbited two stars at once, worlds that were blacker than coal or as light as styrofoam, and even a planet orbiting a stellar corpse known as a white dwarf. Kepler revealed that planets are ubiquitous in the galaxy. If you could place your hand against the night sky, you would likely cover a star hosting at least one planet. The cosmos, it seems, is teeming with worlds, and where there are planets there is the possibility, however remote, of life. But Kepler was just the beginning. In 2018, NASA launched TESS, the Transiting Exoplanet Survey Satellite. While Kepler stared deeply at a small patch of sky, TESS cast a wider net, scanning the entire sky for nearby exoplanets. And in 2021, the James Webb Space Telescope embarked on its mission to study the atmospheres of these worlds, searching for signs of water, methane, and even the elusive fingerprints of life itself. As we drift further into the cosmic expanse, we encounter one of the most enigmatic and powerful phenomena in the universe: black holes. First predicted by Einstein's theory of general relativity, these gravitational monsters are born from the collapse of massive stars. Their gravitational pull is so immense that not even light can escape their grasp. For decades, black holes remained in the realm of theoretical speculation, but in 2015, the LIGO observatories made a groundbreaking discovery. They detected gravitational waves, ripples in the very fabric of space-time, emanating from the collision of two black holes over 1 billion light-years away. Einstein's century-old prediction was confirmed in a cosmic crescendo, and in 2019, astronomers achieved the impossible. They captured the first direct image of a black hole. Using a global network of telescopes, they photographed the supermassive black hole at the heart of Galaxy Messier 87. The image showed a dark centre surrounded by a glowing ring of light, bent and warped by the black hole's immense gravity. It was a stunning triumph of science, and a reminder of the strange and wonderful phenomena that populate the depths of space. But black holes are not the only denizens of the cosmic abyss. In the spaces between the stars, great clouds of gas and dust drift like ghostly veils. These nebulae are the birthplaces of stars, where gravity pulls wisps of gas together until they ignite in nuclear fusion. Like cosmic artisans, stars forge the heavy elements in their cores, the very same elements that make up our bodies and our world. And when stars die, they seed the cosmos with these elements in their final, explosive breaths. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were forged in the hearts of stars billions of years ago. We are, as Carl Sagan famously said, made of star stuff. But the universe is not content with the ordinary. In the depths of space, we find some of the most extreme and bizarre objects imaginable. Pulsars, the rapidly spinning remnants of massive stars, flash like cosmic lighthouses. Magnetaires, with magnetic fields trillions of times stronger than Earth's, could wipe the information from every credit card on the planet. And quasars, the brightest objects in the universe, glow with the light of billions of stars from the very edge of time. As we contemplate these cosmic wonders, it's easy to feel small and insignificant in the grand scheme of things, but in another sense, we are deeply connected to the cosmos. The atoms in our bodies, the planets in our solar system, the stars in our galaxy, all are part of the same cosmic story, a story that began with the Big Bang and continues to unfold to this day. And as we drift off to sleep, our minds can wander to the future of astronomy and the secrets that remain hidden in the depths of space. Will we find life on other worlds? Will we unravel the mysteries of dark matter and dark energy? Will we ever know what lies beyond our cosmic horizon? Perhaps in your dreams, you can imagine yourself as a cosmic explorer, venturing to distant worlds and witnessing the wonders of the universe firsthand. You might soar through the rings of Saturn, watch a supernova explode in a distant galaxy, or even fall into a black hole, wondering what strange realm lies beyond the event horizon. And as you wake in the morning, perhaps you'll carry a bit of that cosmic perspective with you. In the grand tapestry of the universe, our lives may seem fleeting and small, but in another sense we are a vital part of the cosmos, the universe becoming aware of itself. Through our eyes, the cosmos can marvel at its own beauty. Through our minds, it can contemplate its own existence. And through our dreams, it can imagine all the wonders yet to be discovered in the vast and mysterious expanse we call the universe. So let us continue to explore, to discover and to dream. For in the depths of space there are surely wonders beyond our wildest imaginings waiting to be found. And with each new discovery, each new glimpse into the cosmos, we come a little closer to understanding our place in the grand story of the universe. As we ponder the vast expanse of the universe, it's humbling to think about how far we've come in our understanding, and yet how much remains unknown. The story of astronomy is one of ever-expanding horizons, each new discovery opening up new realms of possibility. One of the most profound insights of the 20th century was the realization that the universe had a beginning. The discovery of the cosmic microwave background by Arno Penzias and Robert Wilson in 1965 provided the first tangible evidence of the Big Bang theory, which proposed that the universe began in an incredibly hot, dense state and has been expanding and cooling ever since. Penzias and Wilson were researchers at Bell Labs, working with a sensitive radio antenna. They kept detecting a faint, persistent noise that they couldn't explain. At first, they thought it might be a problem with their equipment. They even went so far as to remove a pair of nesting pigeons from the antenna, thinking their droppings might be causing the issue. But the noise persisted. Unknown to them, just 30 miles away at Princeton University, a young physicist named Jim Peebles was working with his colleagues Robert Dicke and David Wilkinson on predictions of the Big Bang theory. They realized that if the universe began in a hot, dense state, there should be a residual glow, a cosmic afterglow of the Big Bang itself. When Penzias and Wilson learned of this work, they realized the significance of their discovery. The noise they had detected was none other than the cosmic microwave background, the echo of the Big Bang that Peebles and his colleagues had predicted. It was a stunning confirmation of the theory and a landmark moment in the history of science. The cosmic microwave background is a nearly uniform glow of microwave radiation that fills the entire sky. It's the oldest light in the universe, a snapshot of the cosmos when it was just 380,000 years old. At that time, the universe had cooled enough for atoms to form, and photons of light could finally travel freely through space without constantly colliding with charged particles. This ancient light has been stretched by the expansion of the universe over 13.8 billion years, shifting it into the microwave part of the spectrum. When we observe the cosmic microwave background today, we're seeing a distant image of the universe in its infancy. But the cosmic microwave background isn't perfectly smooth. It has tiny variations in temperature and density, and these variations are the seeds of all the structure we see in the universe today. Slightly denser regions had a slightly stronger gravitational pull, and over billions of years they attracted more and more matter, forming galaxies, stars, and planets. In the 1980s, a team of scientists led by George Smoot set out to measure these variations, using a series of increasingly precise satellite experiments. The first of these, the Cosmic Background Explorer (COBE) satellite launched in 1989. COBE made the first detailed full-sky map of the cosmic microwave background and detected the tiny variations in temperature that Smoot and his team were looking for. These variations were incredibly small, Just one part in 100,000. But they were there. It was like looking at a flat ocean and noticing tiny ripples on the surface. These ripples were the imprints of the primordial fluctuations in density that would eventually give rise to the cosmic web of galaxies we see today. Smoot's findings were groundbreaking. They provided further evidence for the Big Bang theory and helped to refine our understanding of the early universe. For this work, Smoot and his colleague John Mather were awarded the Nobel Prize in Physics in 2006. Subsequent missions like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have made even more precise measurements of the cosmic microwave background. These observations have allowed cosmologists to determine the age, composition, and geometry of the universe to incredible precision. We now know that the universe is around 13.8 billion years old, and that it's composed of roughly 5% ordinary matter, the stuff that makes up stars, planets, and us, 27% dark matter, an unknown substance that interacts gravitationally but not with light, and 68% dark energy, an even more mysterious entity that seems to be causing the expansion of the universe to accelerate. We've also learned that the universe appears to be flat on large scales. If you were to draw a giant triangle in space, the angles would add up to 180 degrees, just like they do in Euclidean geometry. This is a puzzling result because it requires the density of the universe to be precisely balanced between being too dense, which would cause the universe to eventually collapse back on itself, and too sparse, which would cause the universe to expand forever at an ever-increasing rate. This fine-tuning of the universe's density is one of the great mysteries of cosmology. Why should the universe be so precariously balanced? Is it just a coincidence, or is there some deeper explanation? As we contemplate these profound questions, it's worth remembering that our understanding of the universe is always evolving. Each new discovery raises new questions and opens up new avenues of inquiry. In recent years, for example, there has been growing evidence that the expansion of the universe is actually accelerating. This was first hinted at in the late 1990s by observations of distant supernovae, which appear to be further away than expected based on the rate of expansion we'd inferred from the cosmic microwave background. This acceleration is attributed to the mysterious dark energy that makes up the majority of the universe's content. But we have no idea what dark energy actually is. Is it a property of space itself? A new kind of dynamical fluid? Or something even more exotic? Similarly, we know that dark matter must exist to explain the gravitational dynamics of galaxies and galaxy clusters, but we have no idea what it's made of. Is it a new kind of fundamental particle? Or something more complicated like a tiny black hole or a fuzzy quantum wave? These are the kinds of questions that keep cosmologists up at night, and yet it's precisely this sense of mystery and discovery that makes the study of the universe so exciting. As we drift off to sleep, let's allow ourselves to be inspired by the great thinkers and explorers who have driven this cosmic journey of discovery. From the ancient Greeks who first tried to understand the motions of the heavens, to the modern scientists probing the nature of dark matter and dark energy, each generation has added to our understanding of the cosmos. And let's dream about the discoveries yet to come. With new observatories like the James Webb Space Telescope, we'll be able to peer further into the universe than ever before, potentially revealing the first stars and galaxies to form after the Big Bang. And with new particle physics experiments, we may finally unlock the secrets of dark matter and dark energy. As we slip into slumber, let's carry with us a sense of wonder at the incredible universe we find ourselves in. And let's be grateful for the curiosity and ingenuity of the scientists who have helped to reveal its mysteries. For in studying the cosmos, we are in a very real sense studying ourselves, our origins, our place in the grand scheme of things, and the fundamental laws that govern all of existence. The story of the universe is ultimately our story, and what a breathtaking, awe-inspiring story it is. As we close our eyes and drift off into the realm of dreams, let's allow ourselves to be filled with a profound sense of connection to the cosmos that birthed us. For we are all made of star stuff, and to the stars we shall return. Good night and pleasant dreams. As we ponder the vast expanse of the cosmos, we can't help but marvel at the ingenuity and perseverance of the scientists who have brought us to this point in our understanding. Their tireless work and brilliant insights have illuminated the dark corners of the universe, revealing a reality far stranger and more wondrous than our ancestors could have ever imagined. One such luminary was Albert Einstein, whose groundbreaking theories of relativity revolutionized our conception of space and time. Born in Germany in 1879, Einstein was a precocious child with a fascination for the unseen forces that governed the world around him. As a young man, he struggled to find a teaching position, working instead as a patent clerk in Bern, Switzerland. It was there, in the quiet moments between reviewing patent applications, that Einstein began to formulate his radical ideas about the nature of the universe. In 1905, Einstein published a series of papers that would forever change the course of physics. In his special theory of relativity, he proposed that space and time were not absolute, but rather interwoven into a single fabric called space-time. Moving objects experienced time differently, he argued, and the speed of light was a universal constant that could never be exceeded. These ideas flew in the face of centuries of accepted wisdom, but they would soon be borne out by experimental evidence. Einstein's insights didn't stop there. In 1915, he published his general theory of relativity, which extended his ideas to encompass gravity itself. According to Einstein, massive objects like stars and planets actually warped the fabric of space-time, creating the effect we perceive as gravity. This mind-bending concept led to predictions of exotic phenomena like black holes and gravitational waves, ripples in space-time caused by cataclysmic events like colliding neutron stars. For decades, these ideas remained purely theoretical, but as technology advanced, scientists began to put them to the test. In 1919, during a total solar eclipse, astronomers measured the bending of starlight around the Sun, just as Einstein had predicted. In the 1960s, astronomers discovered distant objects called quasars, which appeared to be receding from us at speeds that challenged our understanding of the universe's expansion. These observations helped confirm the Big Bang theory and solidified the role of dark energy, a mysterious force that seems to be accelerating the universe's expansion. In more recent years, Einstein's legacy has continued to shape our exploration of the cosmos. In 2015, a century after he predicted their existence, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves for the first time, opening up an entirely new way of observing the universe. By studying these ripples in space-time, scientists can probe some of the most extreme events imaginable, from the collision of black holes to the birth of the universe itself. As we lie in bed, our minds drifting through the cosmos, it's easy to feel small and insignificant in the face of such immensity. But in a way, the story of our exploration of the universe is also a story of our own limitless potential. With each new discovery, each new theory that unlocks another secret of the cosmos, we push the boundaries of what we thought was possible. We stretch our minds to encompass ideas that would have seemed like science fiction to our ancestors, and in doing so, we expand our understanding of our place in the grand tapestry of existence. And still there is so much more to discover. As we gaze out at the night sky, we can only imagine what wonders still lie hidden, beyond the reach of our telescopes and satellites. Are there other forms of life out there, perhaps on planets orbiting distant stars? What might we learn from studying the supermassive black hole at the centre of our own galaxy? And what lies beyond the observable universe, in the vast expanse of space that we cannot see? These are the questions that will drive the next generation of astronomers and physicists, just as they drove Einstein and his contemporaries a century ago. And as we drift off to sleep, perhaps we can take comfort in knowing that somewhere out there, in a quiet corner of the cosmos, someone is working tirelessly to answer them, to shine a light into the darkness and reveal the true majesty of the universe in which we live. The quest to understand the depths of space is one that has captured the human imagination for centuries. From the earliest stargazers who charted the motions of the planets to the modern-day scientists who probe the very fabric of reality, we have always been drawn to the mysteries that lie beyond our world. And with each passing year, each new discovery and breakthrough, we inch ever closer to unlocking the secrets of the cosmos. One of the most exciting frontiers in modern astronomy is the search for exoplanets, planets that orbit stars other than our own sun. For centuries, philosophers and scientists alike have speculated about the possibility of other worlds, but it wasn't until the 1990s that we finally had the technology to detect them. Using a variety of techniques, From measuring the wobble of a star caused by the gravitational pull of an orbiting planet to observing the dimming of a star's light as a planet passes in front of it, astronomers have now confirmed the existence of thousands of exoplanets, with many more candidates awaiting verification. Some of these planets are truly alien worlds, with conditions that challenge our understanding of what makes a planet habitable. There are hot Jupiters, gas giants, that orbit perilously close to their stars, with atmospheric temperatures that can exceed a scorching 1000 degrees Celsius. There are super-Earths, rocky planets several times more massive than our own, with gravity so strong that it would be difficult for humans to even stand on their surface. And there are planets that orbit not one but two stars, real-life Tatooines straight out of science fiction. But among this incredible diversity of worlds, there are also tantalizing hints of planets that might be more familiar. Planets that orbit within their star's habitable zone, where temperatures could allow for the existence of liquid water on the surface. These planets, if they exist, would be prime candidates for the development of life as we know it, and their discovery would have profound implications for our understanding of our place in the universe. Of course, even if we were to find a truly Earth-like planet orbiting another star, the distances involved would make it impossible for us to visit with current technology. The nearest star to our own, Proxima Centauri, is over 4 light-years away, a distance that would take tens of thousands of years to traverse using even the fastest spacecraft we have today. But that hasn't stopped scientists from dreaming up creative solutions to the problem of interstellar travel. One proposed method is the use of light sails, giant ultra-thin reflective sheets that could be propelled by the pressure of sunlight or powerful lasers. By harnessing the power of light itself, these sails could theoretically reach speeds of up to 20% the speed of light, allowing them to cover vast distances in a relatively short amount of time. Another idea is the use of nuclear propulsion, which could provide the sustained thrust needed to accelerate a spacecraft to a significant fraction of the speed of light. But even if we were to develop the technology to travel to other stars, there would still be immense challenges to overcome. The human body is not designed for the rigors of long-term spaceflight, and we would need to find ways to protect ourselves from the harmful effects of cosmic radiation, muscle and bone loss, and psychological stress. We would also need to develop sustainable life support systems capable of providing food, water, and breathable air for the duration of the journey. And yet, despite these challenges, the allure of the stars remains as strong as ever. There is something deeply human about the desire to explore, to push beyond the boundaries of what we know and venture into the unknown. It is the same impulse that drove our ancestors to cross oceans and scale mountains, to chart the far reaches of the globe and beyond. And it is an impulse that will continue to drive us forward, even as we sleep beneath the twinkling canopy of the night sky. As we lie here, our minds adrift in the cosmos, it's worth reflecting on the incredible journey that has brought us to this moment. From the first glimmerings of consciousness to the technological marvels of the modern age, we have come an almost unfathomable distance in our quest to understand the universe and our place within it. And yet, in many ways, we are still at the very beginning of that journey. There are still so many questions left unanswered, so many mysteries yet to be unravelled. We still don't know the true nature of dark matter and dark energy, the unseen substances that make up the vast majority of the universe. We have yet to find definitive evidence of life beyond Earth, or to understand how it might have arisen in the first place. And we are only just beginning to probe the deepest reaches of space and time, to the very edge of the observable universe and the dawn of creation itself. But perhaps that is what makes the exploration of the cosmos so endlessly fascinating. The knowledge that no matter how much we learn, there will always be more to discover. Each answered question only leads to new ones. Each solved mystery only deepens the sense of wonder at the sheer scale and complexity of the universe we inhabit. And so, as we drift off to sleep, let us dream of the wonders that still lie ahead. Let us imagine the thrill of setting foot on a distant world, of gazing up at an alien sky filled with unfamiliar constellations. Let us ponder the possibilities of life in all its myriad forms, from the microbes that might lurk beneath the icy surface of a moon, to the advanced civilizations that could be beaming signals across the vastness of space. Above all, let us never lose sight of the incredible privilege it is to be a part of this grand cosmic adventure. For in a universe so vast and ancient, so filled with beauty and mystery, we are the ones who have the power to unravel its secrets. We are the ones who can peer into the depths of space and time, who can ask the big questions and dare to dream of the answers. So let us embrace that privilege and all the challenges and opportunities it entails. Let us continue to push the boundaries of what is possible, to reach ever further into the unknown. And let us never forget the sense of awe and wonder that comes from contemplating our place in the universe, a universe that is at once incomprehensibly vast and intimately connected, a universe that we are only just beginning to understand. As we finally surrender to the gentle embrace of sleep, let us carry that sense of wonder with us into our dreams. Let us imagine ourselves adrift among the stars, exploring the farthest reaches of space and time, and let us awaken tomorrow with renewed curiosity and purpose, ready to take the next step in our never-ending journey of discovery. For in the end, that is what the exploration of the cosmos is all about. Not just the accumulation of knowledge, but the expansion of our own horizons. It is about looking up at the night sky and feeling a sense of connection to something greater than ourselves. It is about understanding our place in the grand tapestry of the universe and marvelling at the sheer improbability and preciousness of our existence. And so, as we finally drift off to sleep, let us hold on to that sense of connection and wonder. Let us dream of the infinite possibilities that lie ahead and the incredible journey that we are all a part of. And let us awaken tomorrow with a renewed sense of purpose and gratitude, ready to embrace the mysteries of the cosmos and all that they have to teach us. Good night and sweet dreams. As we ponder the vastness of the cosmos, it's humbling to remember that our journey of discovery has really only just begun. In the grand scheme of things, we are like children dipping our toes into the vast ocean of the universe, marvelling at the treasures we find washed up on the shore. Each new discovery, each glittering gem of knowledge, hints at the greater wonders that surely lie beyond our current understanding. In recent decades, our exploration of the cosmos has taken on new dimensions, no longer confined to just catching the light that falls into our terrestrial telescopes. We now send robotic emissaries to extend our senses far beyond Earth. Voyager 1 and 2, twin trailblazers launched in 1977, have now ventured into interstellar space, becoming the first human-made objects to leave our solar system behind. Though their technology may seem quaint by today's standards, these intrepid explorers continue to beam back whispers from the edge of the abyss, reminding us of the ingenuity and curiosity that propel us ever outward. Other spacecraft have sent back postcards from even stranger realms. The Hubble Space Telescope's successor, the James Webb Space Telescope, launched in 2021 and now peers into the infrared, seeing through cosmic dust to spy the oldest galaxies flickering into existence in the afterglow of the Big Bang. Like a time machine, it allows us to witness the universe's infancy, to see the first seeds of cosmic structure taking root. Even as we cast our gaze outward, we've also turned our attention to the worlds next door. Missions like Cassini, which spent over a decade exploring the Saturn system, have revealed moons that defy our earthbound expectations. Take Enceladus, a small, icy moon that conceals a liquid water ocean beneath its frozen shell. Cassini discovered towering geysers erupting from cracks near Enceladus' south pole, hinting at hydrothermal vents on the ocean floor that could, in theory, provide the right conditions for life to emerge. Or consider Titan, Saturn's largest moon, enveloped in a thick, hazy atmosphere and home to methane lakes and rain. It's like a strange, distorted mirror of Earth, inviting us to ponder the diverse forms that worlds, and perhaps life, can take. These discoveries are a testament to the power of human curiosity and the ingenuity we bring to bear in our efforts to understand the cosmos. They also remind us of how much we have yet to learn. For every question we answer, new ones arise, beckoning us further down the path of exploration. We've learned that water, that precious ingredient for life as we know it, is surprisingly abundant in our solar system. But does that mean life itself is common? Or is our pale blue dot a rare oasis? We've detected thousands of planets orbiting other stars, but how many of them might be like Earth? And what strange new forms of life might have taken hold on those alien shores? As you drift off into dreams, let your imagination run wild. Picture yourself walking on the rusty sands of Mars, or soaring through the methane fog of Titan. Imagine diving into the subsurface ocean of Enceladus, or watching the sun set over the ice cliffs of Pluto. In your mind's eye, you might even venture to worlds yet undiscovered, planets and moons that orbit distant stars, waiting for the day when our technology and our restless spirits carry us to their alien vistas. Because that is the promise and the provocation of astronomy. It invites us to dream, to imagine possibilities beyond the bounds of our current knowledge. It humbles us with the realization of our own cosmic insignificance, but it also uplifts us with the reminder that we are a part of something vast and wonderful, a universe of endless potential and mystery. So as you slip softly into sleep, take comfort in the knowledge that above you the stars are shining, cosmic lighthouses guiding our way to future discoveries. We are a part of their story, a species of explorers and dreamers who have only just begun to map the shores of the cosmic ocean. Who knows what marvels tomorrow may bring? And if you've enjoyed this journey through the cosmos, consider liking this video and subscribing to the channel. Every view, every like, is like a little beacon of encouragement, a signal that helps guide more curious minds to ponder the wonders of the universe. Together we can keep the spirit of exploration alive, even as we rest and dream. Because in the end, that's what astronomy is all about, inspiring us to keep asking questions, to keep reaching for the stars, and to never stop marveling at the grand cosmic adventure we're all a part of. So good night, and may your dreams be as vast and wondrous as the universe itself.